Good morning, everyone. Welcome to our presentation on bionic computing, share or call. I'm Zhun representing Wang to give this presentation. So what is bionic computing? In this slide, you can see an image of the humanoid robot software, a great example of AI that's often compared to biological systems. We will delve into discussing how insights from biology can be applied to computing. Here's our agenda for today. We will begin with the core definition of bionic computing, then explore its technical directions, global investment landscape, and typical applications. Finally, we will discuss the current challenges and future trends. So, what exactly is bionic computing? It is an innovative field that integrates biological principles with computer science to create low-power, highly adaptive computing systems. As this table shows, it differs from traditional computing by focusing on how low energy consumptions, self-learning capabilities, and the parallel processing, much like the human brain. Bionic computing is advancing in four main directions. Neuromorphic computing simulates brain neurons, with chips like Intel's Loihe being prime examples. We also have bio-inspired algorithms that draw from biological evolution, brain-like computers that simulate large-scale neural networks, and even biological computers that use living neurons as their core components. Bionic computing is often classified into three categories: bionic process computing, bionic structural computing, and bionic behavior computing. These classifications help us understand the diverse ways we can apply biological principles to technology. And this slide highlights some specific bio-inspired algorithms, such as the genetic bee colony algorithm and the well optimization algorithm. These examples demonstrate how researchers are drawing inspirations from nature to solve complex problems in various fields like engineering, medicine, and energy. A fascinating example here is the algorithm inspired by the fruit fly brain. Scientists observed how flies sense and categorize odors and applied that insight to a computer science problem. This led to a new solution for the nearest label search problem, which is used for tasks like searching for similar images on the web. And this slide connects visual language action of VLM models with bionic computing. While VLA models use robotics and deep learning, bionic computing relies on biological systems like muscles, nerves, and the brain itself. The core idea is to create systems that can interact with the world in a human-like way, integrating perception, language, and action. I'll take an example here. If I want to drive a manipulator to grab a bottle of water, I may use some very good classical method, including calculations of inverse kinematics, for example, in a very efficient way to drive the robotic manipulator. In contrast, if I want to take a bottle of water in front of me using my own hand, even though I can do this calculation, I may not necessarily ask my brain to calculate inverse kinematics. And this observation may lend itself to the idea of VLA. However, one major problem of VLA today is that it requires large-scale computing resources. On the contrary, human beings do not need such an energy for computing. Actually, most large language model related methods today need a vast amount of computing resources, which may not be so healthy for the research community. And for this, bionic computing may provide an alternative solution to help us to end up with a no energy consumption efficient solution. Globally, countries are increasing their strategic investment in this field. The US, for example, has military enterprise collaborations like the DARPA's Synapses project, while the EU focuses on cross-border collaboration through projects like the Human Brain Project. China is also taking initiatives such as the 14th and now 15th five-year plan. Other countries like Japan and Australia are also making some significant breakthroughs. And Russia also has a very strong research foundation with institutions like Skoltech and the national universities hosting labs for the brain and computer interface, namely BCI and the neuromorphic technology, who has long history of projects, especially in EEG and signal processing. In terms of industry, the private sector is increasingly involved. We are seeing private funding from individuals like Potany and companies like Kaspersky who are investing in domestic neuromorphic startups. This strategy's primary focus is on developing domestic alternatives. The goal is to create low-power neuromorphic chips for critical applications, with a particular emphasis on the defense sector and edge AI, ensuring Russia's technological independence in these key areas. Bionic computing has numerous applications. In healthcare, it's advancing brain-computer interfaces to assist paralyzed patients. It's also used in developing intelligent robots and improving the efficiency of autonomous driving systems. Additionally, it's being used in scientific research to accelerate drug discovery. Despite the promises, there are also significant challenges. We face technical bottlenecks such as the stability of biological components. There are also ethical and legal issues, including the unclear standards for using human neurons. Finally, cost and scalability remain a major hurdle. Looking ahead, we can expect increased technology integration, combining bionics with fields like quantum computing and photonics. Applications will deepen, leading to things like personalized healthcare and sustainable energy optimization. Notably, Russia is making significant strides in embodied robotics and extreme environment applications. For example, Russia's state-of-the-art Tenedroid robot can operate both inside and outside space stations. The industry landscape will be marked by an open source ecosystem as a key competitive area. In this landscape, Russia is prioritizing sovereignty in robotics and quantum computing, and fostering cooperation with other BRICS nations. And this section presents some supplemental materials to help us think more deeply about the topic of bionic computing. We will start by looking at a profound insight from Albert Einstein and the fascinating work of Carl von Frisch on the waggle dance of honeybees. These examples provide a useful analogy for understanding the complexity of biological systems. Here we have a famous quote from a letter by Albert Einstein. He wrote, "The intuitive mind is a sacred gift, and the rational mind is a faithful servant. We have created a society that honors the servant and has forgotten the gift." This quote challenges us to consider the value of intuition and the core cognitive processes that modern technology often overlooks, a theme that resonates deeply with our discussion today. This slide introduces the Nobel Prize-winning work of psychologist Daniel Kahneman, particularly in his book, Thinking Fast and Slow. Kahneman describes two systems of thinking. System 1 is our fast, intuitive, and emotional side, while System 2 is our slow, deliberate, and logical side. This framework is a perfect parallel to our presentation's core argument. Much of today's bionic computing is only a sheer or a fast system, and we have yet to develop the core or slow systems that truly mimic the deeper understanding of the brain. To further explore these ideas, we have included some media resources. The image on the right shows the cover of Kahneman's book, a must-read for anyone interested in cognitive science. The image on the left is a link to a YouTube video that provides additional context and insight into these complex topics. They are excellent resources for understanding the concepts we've discussed today. In conclusion, bionic computing offers a key solution to overcoming the limitations of Moore's law and achieving low-consumption, high-efficiency computing. Globally, strategic investment is increasing, and technology is moving from the lab to commercialization. To move forward, we must strengthen basic research, promote collaboration, and establish ethical standards. Thank you for your attention, and we look forward to collaborations.